how to integrate GenAI with system engineering. So we have heard quite a lot about details how to apply large language models. I want to go a little bit back and talk about software in automotive and the needs that we have seen in the last years. So we have a need to develop approximately 1,000 complex functions, varies for vehicles. We develop in the context of evolving EE architectures towards high-performance computing. That means that we cannot use things we have done before. We have to write a lot of new code. Thank you. And we have rising expectations concerning update cycles. And on the same time, we have much higher requirements concerning functional safety and cybersecurity compared to consumer devices. So what have people presented as selected approaches to deal with the situation in the last years? So if you look back at conferences about more than 5 years ago, 2018-19, people were talking about we need to hire more software engineers. And people were standing up and saying, look, we managed to hire 1,000 software engineers. Wow, what an achievement. At the same time, a lot of the standardization was taken care by proven frameworks like AUTOSAR Classic. You reuse modules that others have written for you. Then if you look 3 years ago, what happened 3 years ago? Even companies were hiring more software engineers, and there have been several open source initiatives being mentioned and the intention to use more open source. So besides the proven AUTOSAR. So it's like a swarm effect. We put resources together to become more better and faster. Now what we see, just 1 or 2 weeks ago, there was again a new project announced, the S-Core project, now bundling together BMW, Mercedes-Benz, Volkswagen, ZF, ETAS, Bosch, Valeo, Vector, where I'm from, Elektrobild and Corix under the coordination of the VDA. So it's again an open source approach to answer the question, how can we create so much software altogether and still be competitive? But on the same time, now we are talking a lot about GenAI. GenAI for code generation and GenAI for other processes in automotive development. My presentation will focus on this later effect here, and let's look a little bit back where I come from, where I draw my experience from, and how it translates to today. So I was involved in the 80s and 90s in AI development. You see here, this book, Parallel Distributed Processing, was really the starting point of the AI we see today. At that time, Geoffrey Hinton was at Carnegie Mellon, and last year he got the Nobel Prize for his achievements with AI. And at that time, I was also at Carnegie Mellon University and had the chance to be part of these, let's say, growth of ideas. I was working on speech recognition and speech translation. And at that time, in '94, we could have something like that. You speak to the computer, it was translated, and somebody on the other side could listen to it in his or her language. If you look at the picture, it looks like a Teams meeting today. But in fact, 30 years ago, it was, let's say, something not normal. It was hard work to bring this up, to have a speech recognized, and so on. The commercialization of that started then. Let's say in 2013, such systems were brought to your phone, and this was called GBGo and then was acquired by Facebook. But what we learned from that over several decades, that something that started 30 years ago has now become daily life, daily experience. Everybody talks to phone, talks to cars. And it's based on AI, and we cannot do without today. It has become part of our life. So now, today's large language models, and we have seen quite a lot about that in the previous presentations, by their heart, they are natural language processors. And they deal, or they were built to deal with natural language. And natural language is by heart a non-formal language in contrast to code. It's spontaneous and it's ambiguous. But the good thing is that OpenAI proved that first, that it can be very successfully applied to something like formal language creation. That means code generation, which is not natural language. It does not have these ambiguities. But of course, the natural language processors can deal with that. And the strength of the current generation and the evolution that has taken place over several decades now is that we are able to capture a real long range of context of single words, because this is also part of natural language. Something can change the meaning of a sentence completely. And the mix of supervised and unsupervised training facilitate the use of really, really big data. The provision of huge computational resources then can facilitate the training with big data. And it is the combination of strong ideas and hard work developed over a long time. It's the effect and the result of several decades by various teams and individuals from an open and also very competitive AI ecosystem. I consider this a very open ecosystem. You can get a lot of information for free. You can get a lot of code for free. But on the other side, if you look at the big players, it's really also competitive. It's not easy to survive in this ecosystem. So now if you look at the development of such natural language processing systems from 87 to now, you will see small systems at the beginning, 6,000 parameters, very limited training data, and it grew dramatically to what we experience today, billions and trillions of parameters, and really a lot of data needed to train such a thing. And something that comes with it is expenses. So we see OpenAI in 2022 spent 76% of their spending on computing and data, and 16% on staff. I think for automotive, it's way the other way around. It's just different. And by doing that, or in order to pay for that, you need a high number of use cases. You cannot pay for that amount of money with just using something 50, 100,000 times a year. You need millions of users and you need millions of use cases. And this is the business. Its amortization is by a very large number of use cases and repetitions. So now let's come to our automotive engineering processes. And let's have a look, where do we find a high number of use cases and a high number of repetitions? Of course, it's in requirements. First of all, we have 10,000, 50,000, 100,000 requirements. And we do not touch only one time, we touch them several times in a project. Because they get changed, they get analyzed again, and so on. So this is high volume of interactions here. Secondly, code generations. We have 100,000 millions of lines of code that need to be generated. We have 1,000 functions per vehicle to be developed. So that means a lot of code, a lot of software units. And the experience is they are not only touched once, they are touched several times because they need to be adapted, corrected, or whatsoever. And last but not least, testing. We have 10,000, 50,000 test cases, and with every integration, with every release, this has to be tested and touched again. So this is where the volume is. For the other processes like architecture design, like integration, they're important processes, and it's important to know how to do them well, but they do not have these numbers behind them. So my recommendation is, if you look for something applying GenAI to your processes to become faster, to become more cost efficient. Apply GenAI to the most frequent activities with a high amount of data, because you will need that to train also. So then when this came out, OpenAI showed nice results with prompts. You just put in a prompt and you generate code out of it. It was stunning. And now, as a result, many teams around the world are trying to use that and also apply that in their development. And we see the greatest activity right now in code generation. But now, I mean, how do we combine that with our system engineering approach? What do I mean by system engineering approach? Well, we have a set of processes, and by using a certain logic, we have a set of processes that are more than the individual processes. And they are kind of logically connected, they support each other, and together they make more sense as if they are done alone. So also, if we look at writing of code, so the ability to write code exactly according to the requirements and architecture distinguishes the experienced software engineer from the beginner. So if you have students who have never worked in a big team, they certainly know how to write 3, 4, 5 lines of code. But to bring this in a larger context of software, in a larger team of hundreds of software engineers, you need the experience, you need to understand the requirements, the architecture, the interfaces, and so on. So then, if we would use then a large language model and the automotive system engineering methodology, and we would create a prompt, and how do we bring the software requirement analysis and the software architectural design and the detailed design into that prompt? That is now the question. Because we think we have this methodology of doing requirements analysis, of doing architectural design, detailed design. This is our proven methodology. How do we bring this into the prompt? That is the question. And because we have learned, software is much more than just writing the couple of lines of code. Software engineering is much more. So, in order to discuss that with you, I have defined 5 options, and let's go through the options one after the other to see what it is. Option number 1 would be to simply say, waive the system engineering philosophy completely and forget about it, we just write prompts. So that would mean we wipe out the complete left side of our processes, we just write the prompt, but then the problem comes. How do we integrate the snippets of code into the rest of the code that are generated by others, that are available from legacy, and so on? How do we integrate that? How do we test it, and so on? Honestly, I have experienced situations like that 20, 25 years ago, when there was no such solid system engineering, and you had integration weeks where one guy was striving to bring simple code together. I don't want to bring these puzzle pieces together again, so let's forget about it because the experience was not so good and would not fit to the complexity of our software today. Now, option number 2, adapt requirements engineering and architectural design to better fit to GenAI. So what do we see here? On the one hand side, we have requirements engineering, a solid discipline that has evolved over several decades now. And on the other hand side, we have prompt engineering, a new discipline that is coming up. And on the first level of requirements engineering, you see templates that allow you to write unambiguous code with natural language. When, who must do what. It's a very simple template. It's an IEEE template to write good requirements, and it really helps to write natural language requirements. And the same happens exactly in prompt engineering, because many people are right now talking about how do you have to write a prompt in order to get what you want. Still, the results may vary. You may want to try around a lot, and often what you feel, I have to extend the prompt. I add elements to it, and then I'm getting closer. That's the first level. Second level in requirements engineering then was this semi-formal requirements where you had inputs, outputs, sequence information and so on to the requirements in order to get more concise information. And the same thing happens in prompt engineering now. We're talking about few-shot prompting. You add examples or demonstration and the in-context learning. So just with your prompt, you add quite a lot of information in addition to it. And you have provide a context to your prompt in order to allow the model to do a better inference. And because it has been so important and powerful, the models are now striving hard to allow to put in longer context. And currently the limit is around 128,000 tokens. A token roughly is a word or something like that. And that means, wow, 100,000 words of context. That sounds, that sounds powerful, but that sounds kind of not so clear what that means. But this is the second level of, and you see how well requirements engineering and prompt engineering match to each other. On the next level of requirements engineering, we then had these diagrams, activity diagrams, sequence diagrams, state diagrams, in order to make things clearer, things that you cannot explain well with just words. No, a picture sometimes tells a lot more than a single word. So, and the same thing happens in prompt engineering as a chain of thought prompting. You give a logic, you have a branch structure, and so on. So what we see here that things are evolving very similar. Prompt engineering is evolving very similar to requirements engineering. So I can say this can be adapted. We can live with prompt engineering because it's so similar to requirements engineering. Now let's look at architecture design. If you look into the original information, how OpenAI built the first code generation in 2021. They have 54 million of repositories, and they just take the code of these repositories. Then they do some filtering, some minor filtering in the repetition, 60 gigabytes of pure text, but they never mention architecture. They never mention a single word about architecture. And if you know public GitHub repositories, you know why. Because architecture and, let's say, the traceability from software elements to architecture is never a big topic in public GitHub repositories. It's traceability. And traceability, you know, it's hard to maintain. And, you know, from iSpace assessment, sometimes the last gaps you have, the missing traceability. It's hard to maintain good traceability. So what is in such a large language model that has been trained with this tons of data is a conglomerate, a vast conglomerate of architectures, underlying architectures. And there is no a single architecture, there's no specific set of architectures. It's just by any chance, by random, the architectures the authors selected. So this is not adaptable to what we are used to. We are used to have a dedicated architecture in our system. So yes, we can adapt to this requirements engineering, but no for this software architecture design. So now option number 3 include requirements and architecture in the training. So that means usually we train with code only, but we could train such a large language model with a triple of requirement, architecture element, and code. And if we would do that, then the large language model would learn the architecture element and the requirement. So we would have the appropriate information all together. Unfortunately, in the publicly available repositories, this combination is not available. They don't put it there. Maybe we have it inside our companies. We have, if we have good data management, configuration management, traceability, we have it in our companies, but Usually this is not available in the size that we're talking about here. So let us bundle resources together and create a specific auto AI. So we take this idea of having these triples of information, requirement, architecture, element, code, and we put together creation partners, companies that really drive this forward and develop such a large language model, and contribution partners who provide the data points from requirements, architecture, element, and code. And we have an asset pool, we have a data pool, we have a resource pool to build a tool that only knows a standardized automotive architecture. That would be possible because it's possible to learn these all together. Yeah, it requires an important initiative, which currently is not visible, but it would be possible to build something like that. Then we have option number 5, to include the requirements and the architectures by in-context learning. We have heard about that. So in principle, what you can do is that you provide huge context to these very powerful models, 100,000 words, 128,000 words. Sometimes it doesn't work on these limits, but in theory, the ability is there. So what we would do, we take all the requirements in natural language, we take all the requirements in diagrams, and we convert that to text files. It's some kind of re-engineering. So if we forget about all this graphical information, we just generate a long text file. And in this text file, then we add also, let's say, the architecture description. It might look something like converting a map into a text file. Imagine a text file describing all the streets of Stuttgart. It would be horrible to read. But in principle, it's possible. So I've seen people trying that, and the result is really long. If you look at typical automotive projects, you get into this range of 100,000 words, even more is possible. So in theory, this is possible to process that. Your projects, you have your prompt, you have 100,000 words of text describing all your requirements and architecture, and then you can use this GenAI for your code generation. So a very promising option, but now let us have a look at the food chain of artificial intelligence. So currently what we are seeing, that there are a couple of players who have the resources, the people, the hardware to train these top range models, and they are independent. And we see several AI tier 1s that use that. They further refine it, they develop based on that. So it's very similar to our OEM and tier structure. And we know all the advantages to be on the top. We all know also the advantages to be somewhere in between, but we also know the challenges for that. Certainly, money goes from bottom to top, and terms of use go from top to bottom. And there are some disadvantages, of course, associated with it. So, and this option number 5 would be certainly a tier 1 or tier 2 positioning, and only option 3 or 4 would be then the OSP, or original AI provider positioning. So let me come to my conclusions. First of all, AI and GenAI can become a game changer for our industry, and apply it to the resource-intensive work packages where you have a lot of data, a lot of repetition, and a lot of use cases. For the others, it's not really worth developing this, but where you have repetitions, requirements, test, and code generation, go for it. Secondly, consider the food chain. If you want to stay independent with this, if you want to benefit from being on yourself and being independent, then you need to be one of the original AI system service providers, and that is then you're very likely not liking this option number 5, though it looks very promising. You have to develop something by yourself. You've seen that from Porsche today. Presentation number 1 was very much in this direction. And I'm really appreciating that, because I think it's important that the automotive industry is being a strong AI player and not in this tier 1 or tier 2 position where we are really depending on the few big players who really build the big systems. So thank you for your attention at this late time in the second day of the conference. Thank you very much. And needless to say, Vector supports you. Thank you.
Thank you very much. Thank you very much. What a final, and yeah, we are open for questions.